In this video, I am going to derive the acceleration due to gravity, that 9.8 meters per second squared that we've been using thus far this semester. Okay, to do that, I'm going to use the law of universal gravitation. And so here is the scenario that I am thinking about. I have the Earth. You can tell it's the Earth because it's got a big E in the middle of it. Right? And I have another object, say a ball. Oops. Very near the surface of the Earth, right? The force between the Earth and the ball is given by the law of universal gravitation. That tells me that it is that constant g times the mass of the Earth times the mass of the ball divided by the distance squared. Now, what is the distance here? Well, in this case, you're measuring the distance from the center of the Earth to where the ball is. But if the ball is near the surface, so what do we mean by near the surface? Well, obviously the International Space Station is not near the surface, right? Mount Everest is questionable, but for all intents and purposes, whatever is going to happen during a baseball game, close enough, right? So we're talking the radius of the Earth plus maybe a couple hundred meters. Okay, now you can either ask Dr. Google or you can look in the back cover of Kirkpatrick and Francis here, and you see that the radius of the Earth, I'll write it down here, is 6.37 times 10 to the 6th meters. Okay, so now think about it. Radius of the Earth is 6 million meters. 6 million meters and a change. And we're talking, maybe a couple hundred more. Do you think that couple hundred really matters in the great scheme of things? Not really. So we're going to call this distance just the radius of the Earth. Okay, to do this, we also need to know the mass of the Earth, which again, you can find by looking in the cover of your book, or you can ask Dr. Google, whatever makes you happy. So that's 5.98 times 10 to the 24th kilograms. Okay. Now, let's look at the free body diagram of the ball. Only one force on it, assuming we ignore air resistance. Up to now, so last week we would have called that the weight of the Earth on the ball. And let that have a value of the mass of the ball times that acceleration due to gravity, mg. And what I want to do is reconcile this form with the form for the gravitational force given by the law of universal gravitation. Okay. So it doesn't matter what the mass of the ball is because that's in both formulas. So the real question was, if I look, all of this has to be the equivalent of g. So does g equal g times big G times the mass of the Earth divided by the radius of the Earth squared? Okay. In other words, does that combination of parameters, the universal gravitation constant, the mass of the Earth, and the radius of the Earth, when you multiply and divide them properly, does that come out to give you that 9.8 meters per second squared? So let's plug in numbers. Big G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The mass of the Earth is 5.98 times 10 to the 24th kilograms. We just looked that up. And the radius of the Earth is 6.37 times 10 to the 6th meters squared in the formula. So, pull out our calculators and start putting this in. 6.67 times 10 to the minus 11 multiplied by 5.98 times 10 to the 24th and divide by 6.37 times 10 to the 6th squared. And that gives me out a value of 9.83 meters per second squared on my calculator. So indeed, we can get the form for the gravitational force that we used last week from the new form of the gravitational force we've learned this week, because little g is the combination of big G times the mass of the Earth divided by the radius of the Earth squared.